welcome back, everybody, to another session of the Ethereum Protocol Fellowship Study Group. This is week 7 on the research track, and today we have 3 guests with us, Ignacio, Guillaume, and Josh from the Stateless team at the Ethereum Foundation, here to talk about the Verge, which consists mostly of the upgrade to Verkle trees. So yeah, I don't know, Mario, how you want to do this introduction here for all 3 of them, but good luck.
Yeah, thank you so much. Thank you so much, guys, for joining us today. Yeah, it's pretty heavy on introductions. I probably won't spend too much time on it. Just want to welcome you all to the research track of this week. The Verge, the Verkle trees are a very interesting topic, very important topic happening right now, and it's kind of hard to grasp if you don't have the cryptography inside and the Verkle trees background. So we have 3 speakers today to cover their parts of this research. It's Josh from the EF research team. But Josh haven't been just Ethereum researcher. He's been doing a bunch of cool stuff even before, I believe. He worked in Intel and Slack and many interesting projects. Guillaume is actually from Get team, from the Go Ethereum team. So he contributes to Get, but mostly works on this Verkle tree migration transition. And Ignacio is from the EF research as well. However, the interesting piece about Ignacio is that he actually has been fellow in the EPF cohort 3. So he's the prime example here of a successful EPF fellow, somebody who's been diving into Ethereum and studying this similarly to many people in the audience now. And today he's on the cutting edge of these technologies. So it's honored to have you here, folks, all of you. And I'm very excited to see your presentation. I hope we'll manage to coordinate. So who's starting? Who will kick it off?
I will start.
Okay, go ahead. The stage is yours.
Okay, thank you. Okay, well, first of all, thank all for being here. We are pretty excited that more people are interested in Verkle trees. So this presentation aims to be some, let's say, technical introduction to the topic. We won't expect everybody to understand 100% of what we'll show because many of these things are pretty hairy, and probably if you're interested in this topic, you will come back to these slides after the talk. So just to talk a bit more about our team. Our team is composed of Guillaume, which is the team lead, and also part of the guest team. Then it's Ignacio, which is me. Then we have Josh that also help us with all the community organization, calls moderations, and interacting with other teams because the Verkle tree change really has a lot of impact. And also we have Kev that is related to a lot of work in the cryptography side. We also maintain a website, which is verkle.info, where it's kind of a landing page for the Verkle tree change, where you can find what Verkle trees is about, what is the motivation, which is the current tasks that we and others are working. And also we have some links to some articles and videos where we talk about Verkle. So let's start a bit with the motivation of the change, which is probably the correct way of trying to understand any kind of change in the protocol. Because at least with big changes, they are usually rooted in kind of defending important values of the Ethereum protocol. So if we kind of take a step back and think about systems or applications in general, stateful applications are usually pretty complex. Usually the state part of the system is what creates many of the big challenges, such as how do you access the state in an efficient way, how do you save the state, because usually the state of the system is where most of the value is. So stateful applications are usually pretty complex. And usually state only grows with time, which is usually a pain and something that creates many problems. But if we think about what state means for the Ethereum blockchain, the important effect is that they put a lot of pressure on some core values that we want to defend. Being more concrete, if you want to be a node and validate blocks, unfortunately, you will need first to download all the state of the network, which is somewhat big, so it takes some time. And that means that you also have to save it somewhere, of course. And from some numbers that Guillaume told me in his setup, you will need about 1.5 terabytes of disk space. So probably a good recommendation is having a 2 terabyte disk. This requirement will only increase with time, which is very unfortunate. And also the way that Ethereum handles state isn't CK friendly, which also gets a bit in the way of even more future changes that we want to make to the protocol. So let's think about how we can have a better stateless world. The ideal goal here is that whenever a node wants to join the network, it doesn't have to sync all the state. And indirectly, that means that you don't need like a huge disk for storing all the state. So the main idea is that you download the execution client and the consensus client, you configure everything, you join the network, and you can start validating blocks as fast as possible without requiring a big disk. Also, part of doing this change is trying to make the protocol more CK friendly. So in the future, we can use snarks to create proof of computations as to validate that the block execution has been done correctly. So the main idea is that Verkle trees kind of solve the storage problem of nodes. So at least a stateless client can avoid having even a separate storage for Ethereum state. And in the future with snarks, these nodes can even just verify a computational proof that the block is valid instead of doing the actual execution themselves. So this is going in the direction of trying to reduce hardware requirements for nodes. It also simplifies anyone that wants to try building a stateless client, because if you don't have to deal with storing a big state, you don't have all this complexity of efficient ways of storing things in disk, how to access this data efficiently and all that. You can simply access data that just fits in memory. This change also allows potentially to increase the gas limit, which is like a hot topic now. This isn't something that we'll do in the Verkle fork, but it's something that maybe it will be allowed in the future. And finally, this change is also might be pushing in the direction in which different nodes might have different, more like specialized roles in the protocol, which can have some interesting impact in the staking for nodes. But yeah, that's more like a research area. So if we want to explain how Verkle trees work, or what is like a simple way to explain this change, is that Verkle trees basically introduce something new in the protocol, which is called an execution witness. And this execution witness basically contains all the data that you need to verify a block. So the reason that today you need to download all the state before verifying blocks is that Whenever you receive a block, let's say that you have a single block, and this block has a single transaction in which I send 10 ETH to Mario. So if you want to verify this block, that means that you will need to know my current balance, because if you don't have that, you cannot really verify that sending 10 ETH is a valid transaction, right? And since you cannot really predict which will be the transactions in the next block, that basically means that you need all the state to be sure that you can verify the next block. So the idea is that whenever like Verkle tree happens, you can receive some extra data apart from the block, which is called the witness, which contains all the state that is accessed in this block, such that everything that you will need to validate the block will be found in this witness. This isn't really a new idea. This is something that has been explored before. Even you can do this with the current tree. But the problem is that you cannot really trust whoever gives you this data, because this data can be anything, right? I can simply invent that my balance is whatever, and if you simply trust this witness data to validate the block, you might reach a false conclusion that the transaction is correct when it isn't. So what is needed is a cryptographic proof that this witness data is correct, which is basically similar to a Merkle proof. But what Verkle allows is making this cryptographic proof be really small, such that the complete witness size is small enough to make this viable. And another really interesting thing is that this witness also contains all the code that you will need to execute contracts, which is something pretty weird for people, because they don't actually know that the contract code doesn't really live in the tree. So yeah, to validate a block, you don't only need like balances and storage slots, you actually need the contract code. So making Ethereum stateless sounds interesting, but unfortunately it isn't really a simple task. We need to introduce a new cryptography stack. We need to introduce a new data structure. We have to do some gas accounting changes. And we have to migrate all the data from the Merkle-Bartusha tree to the Verkle tree. So now we will explore all these points in more detail. So let's start with the cryptography, which is the thing that is at the lowest layer. As usually happens in blockchains, whenever you think about some new super cool feature that seems almost impossible, you will find that there's like a cryptography scheme that is really what allows this magic to happen. And in this case, for Verkle trees, the magic happens in this cryptographic proof that the witness is correct, while having this proof size be really small. So this is allowed by the cryptography that is used in Verkle trees, and it's really what allows this witness to be transmitted with each block, which is something that should reach every stateless client. And ultimately, this is what allows Ethereum to continue being a trustless protocol. So each stateless client can verify the block without trusting any other party. And this is done because this cryptographic proof really gives this stateless client the guarantee that this data is correct without trusting other parties that have the full state. The basic ingredients of the cryptography are vector commitments, inner product argument, and multiproofs. So we will talk about them next. But before doing that, let's try to do a refresher on what cryptography we use today in the state tree. So today we use something called the Merkle-Patricia tree, which probably you have heard before. And the kind of cryptography used here is pretty simple. We simply use Keccak cryptographic hash function. And the way this works is like similar-ish to a Merkle tree, but we have like a different kind of data structure with a different branching factor. So instead of a branching factor of 2, Merkle-Patricia trees have a branching factor of 16, have these extension nodes, and the way you kind of point from one parent to the child, you hash the node. So hashes are a way of doing something called content addressing, which is a really deep and important concept in blockchains. So hashes are like pointers that define kind of the identity of each node. But like the TLDR is that we use Keccak for like the cryptography of the Merkle-Patricia tree. In Verkle trees, we stop using Keccak, and we use something that is called vector commitment. So the idea here is that we have vectors of 256 elements, and each item of this vector is a scalar field element. So this is like maybe a technical term, but you can think about this as like numbers. Okay. And we have a commit function, which allows you to provide this vector and receive what we call a commitment. Okay. This commitment is like something similar to a hash in the sense that it's binding. So what binding means is that if you change anything about the vector, this commitment will change. So you cannot really fake. After you have a commitment, you cannot really find another vector that maps to the same commitment. So that is kind of a really important property. Something else that you can do is you can use these prove and verify functions. So these functions, the proof function basically receives a vector and an index, and it will generate pi, which represents a proof that the element at that index is whatever value is in that index. Okay, so basically you can prove that the element at position 2 is 10 or whatever. And you also have this verify function, which receives the commitment of the vector, the index, the claimed value that is in that index, the proof, and it returns false or true depending if this proof is correct that the item in this index is that value. Note that in this verify function, what the verifier needs is only the commitment. It doesn't need the vector, which is where the magic happens. Okay, so the magic here is that you can verify an item in the vector only having the commitment and this proof that is much smaller than having the full vector, right? That's kind of the main point. Going more into the gory details, this vector commitment and proving scheme is used under a setup of a new elliptic curve that we introduced in the protocol, which is called Bandersnatch. We also use another abstraction on top, which is called van der Wagon, to remove the cofactor and make the group safe. The scalar field of this curve is 253 bits, and the base field is 255 bits. This elliptic curve doesn't have pairings, which is good because that means smaller fields, so the operations can be more efficient. And this Bandersnatch curve, it was created with an intention of being what is called an embedded curve in the BLS12-3H1. So basically, the base field of Bandersnatch is the scalar field of BLS12-3H1. The reason for this is that If you want to do snarks using BLS 123H1, that means that the elliptic curve operations in Bandersnatch are basically native field operations. So in a circuit, you don't have to emulate fields, which is really inefficient. This inner product argument is what is like the proving scheme that we use for these vector openings that I showed in the previous slides. An important property is that it doesn't require a trusted setup. So if you kind of compare it with KCG commitments using blobs, that requires a trusted setup, which adds some extra overhead whenever you are doing the configuration of the proving scheme. So we don't have to do that for Verkle trees, which is nice. And we use an extra proving scheme on top, which is called multiproof, that allows to aggregate multiple openings in a single one. So that is really important because it makes the proof even shorter. So let's go now to the data structure and try to understand more how the Verkle tree data structure works. So the change in the data structure of the Ethereum protocol, it's basically switching from the Merkle-Patricia tree to the Verkle tree. The Verkle tree name comes from a mix of vector commitment and Merkle tree. So hopefully now that makes a bit more sense. So if you remember how these trees are used in the protocol, I think that there's a really nice image here in which you can see that if you see the state root of the block header, that is the state root of the world state tree. And basically this tree is a tree of trees. So in the leaf nodes, we have EOA accounts and smart contract accounts. So for EOA accounts, you have basically the nodes and the balance. But for smart contracts, you also have the storage root, which is basically the root of another tree that holds all the storage slots of that contract. So that's why we say that this is like a tree of trees. So this is kind of how things look like for the state storage in the protocol today. This will change. So the first thing to say is that we will stop having this tree of trees. We will have a single tree. So we will have all the balances of accounts and all the storage slots of all contracts all in the same tree. So that's kind of the first big difference. The other big difference is that the tree shape is pretty different too. We have here an image that I took from a really nice article that I invite everyone to read in more detail. I left here the link. So to explain this a bit, we basically have two kind of nodes. We have internal nodes, which have a branching factor of 256, which is another change, another different compared to the Merkle-Patricia tree, which has a branching factor of 16. So this increase in branching factor allows the tree to be shallower, which is really nice because that means that if you kind of think of analogy from a Merkle-Patricia tree, a Merkle-Patricia tree usually has a branching factor of 2, so that means that you need log in base 2 elements to really create a proof. And if you have a branching factor of 256, then you have log in base 256 elements. So that is much better for size. And apart from internal nodes, we have what we call extension level commitments and suffix level commitments. Basically, the idea here is that the tree keys are 32 bytes, so that is the same as today. And the first 31 bytes defines a stem, which is a path to these extension level commitments. And then in each leaf node, we have 256 values. Okay, so basically keys are grouped in groups of 256 values. And the way that we kind of encode them in leaf nodes is with this image that I have here at the bottom, which basically we do like a vector commitment of these elements. We have to do some really tricky construction of having two vectors to really store 256 values. And the reason for that is that, as I said before, the scalar fields are 253 bits, but unfortunately the values that we store are 256 bits. So that means that we need two elements, two scalars per element. But that's kind of a really hairy detail maybe. But I just wanted to explain a bit why we have two vectors to store 256 values. So if we compare the Merkle-Patricia tree with the Verkle tree and how this might affect the proof size. So if you look at the left-hand side image, which I took from an article from Vitalik, the thing here is that despite that the branching factor is 16 and you have like a semi-shallow tree, you still need all the nodes data to really create a proof. Because since we are using hashes and you need to verify the node bytes with the expected hashes, we basically need to hash all the node data. And that means that even if the branching factor is 16, that means that in each node you have up to 16 values, which can be really big. In the case of Verkle trees, since we are using this vector commitment proving schemes, you don't really need to provide all the vector. So if you remember, the verify function only requires the commitment, a small proof, and the index and value that you want to prove, but not really the rest of the vector. So that is really nice, because that means that even that we are making this branching factor bigger, that doesn't really have an impact on how you can prove a single element of that vector or that node. So that's kind of at the core of why this thing works. Okay, so let's jump now to talk a bit more on how information are stored in leaves of the tree. So if you remember, the leaves of the tree are vectors of 256 elements. So we store the usual balance, knowns, the code hash, and like general information about the account. In the case of smart contracts, we have more space to store some extra things. In the current DIP, what we store are the first 64 storage slots, and also the first 128 code chunks. And I will explain what a code chunk is soon, but just bear with me. So the idea is that the what we call the account header, so the leaf node that corresponds to an account, it has the kind of the same information that we have today. And in the case of smart contracts, we leverage this extra space to pack their probably information that will be accessed, which is like where the code starts, well, like the start of the code, and like the top, like the first storage slots, which are probably used with some high probability on transactions. The rest of storage slots and the rest of code chunks are still stored, but not really in the leaf node of the account. They are stored in other leaf nodes that I will explain that later. So I touched a bit here on this concept of code chunks. And if you remember on the one of the first slides, I told you that the execution witness, apart from balances and storage slots, it had also to include the necessary code to validate the block. So that goes full circle here, in which you should know that the contract code is chunked. So chunking the code is part of the process of how the code is stored in the tree. And the way this works is that we basically group, we basically slice the contract code in 31 byte groups. And with that, we create 30, like a value of 32 bytes, where the first byte is a special byte that we use to really solve a particular problem that I will explain now in a minute. But basically, if you look at this image, you will see that a 32 byte code chunk has this first special byte and then 31 bytes of the code. The next code chunk has this extra byte and the next 31 bytes. You do this until the end of the contract code. So if you also remember, there are some instructions in the EVM that require more than 1 byte. So for example, if you do a push to instruction, that means that, or push 10 or whatever, you might find that whenever you do this chunking, there might be some bytes that are part of one chunk, and there are some other bytes of the same instruction that are in the next chunk. So this extra byte is basically trying to signal how many bytes from this code chunk at the start are really a continuation of a previous push X instruction in the previous chunk. But it's just only that, so it's not really that complicated, or at least more complicated than that. All right, so today, whenever you want to access some state in the tree, in the Merkle partition tree, you basically use the kcheck hash function to calculate what is the tree key for that account. Okay. For Verkle trees, we don't use kcheck. Again, it's not zero knowledge friendly, or it's not really snark friendly, let's say. So we cannot really use kcheck. What we use is something, it's kind of an elliptic curve based hashing function, which is called person hashing. And it's basically explained by this kind of definition I give here. I use some colors to really help in the understanding. So the way this works is that we have a tree key function that receives the address of the account that you want to access some state, some tree index value, and some sub-index value. Okay, this tree index and sub-index are names that you probably doesn't make any sense to you, but hold a second there. So the way this tree key function works is that it is basically doing a vector commitment of a vector of size 5. So we have the first element is this fixed number that has a reason, but let's just take it as a fixed number. The next item is the most significant 16 bytes of the address. The next one is the 16 least significant bytes of the address. And we do the same with the tree index here. Okay, so this commitment give us a 32 byte value. And we basically take the first 31 bytes and we append the sub-index, which is a single byte. So we have a 32 byte tree key. Okay, so this is a very abstract function in which receives the address related to the state that you want to access, and these two values. Okay, and you kind of have the tree key. Okay, let's try to think about this in a concrete example. Let's say that we want to know the tree key for the balance for an account. Okay, so what you have to do is you have to use this function that we explained before. You put here the address corresponding to the address that you want to know the balance. You will use the tree index equal to 0. Okay, this is by definition. And then you put here which state you want. In the case of the balance, you will have to put a 1 here. Okay, but each part, if you see here, each kind of state of this account has a different sub-index, where the sub-index is basically which index in the vector you want to access. So in the case of balance, it's 1. In the case of nonce, it's 2, and you can find this in the IP. Okay, and you do this calculation, and you have the tree key, and you can access that in the tree and find what you want. If you remember, in the account header, we also stored these special storage slots and these first call chunks. So if you want to access the storage slot 0, you basically do the same as you do here, but you put the correct index, and the same with these special call chunks. For the rest of the storage slots that are in the first 64, and for the rest of call chunks that are in the first 128, you have to do some other calculation, which is also explained in the IP, which gives you the way to calculate the tree index and the sub-index for that storage slot. Okay, and the same with the call chunks. Let's say that you want the call chunk 1000. So you basically put 1000 here, you add which is this constant, you have this chunk ID. With that, you can calculate the tree index and the sub-index, and you do the tree key function that we explained in the previous slide, and you get the tree key. Okay. This is like maybe the part that is a bit more complex, and it might take some minutes to digest this. So if it sounds confusing, don't be worried. Just try to come back to the slide later, and hopefully it will make some sense. The main idea of adding these constants for storage slots and call chunks is basically a way of partitioning the address space for this address, so these both don't overlap. Okay, because this is really a big number. That basically makes these three indexes not really overlap for storage slots and call chunks. Okay, so now we will switch topics a bit and talk about gas accounting. I think that Guillaume is here, and maybe he wants to continue.
Yeah, I don't know if you guys can hear me.
Yeah, we can hear you, but maybe before we switch topics here, a couple questions in the chat here that might be relevant.
Sorry, before we get to the questions, I just had one comment to give to the previous slide.
Sure, great.
Yeah, it's just that, the main storage offset is really big, but on top of that, the code size itself is limited. We want to increase the size of the code, but we will never increase it to the size of main storage offset. So there should never be a clash, basically.
Got it. Thank you. Would you be willing to walk through quickly how retrieval changes with Verkle trees compared to Merkle trees? Question is like, what's the benefit of calculating the extra commitments?
You mean like the performance overhead of Verkle trees compared to Merkle partition trees?
I believe so. When you're retrieving data.
Right. So Verkle tree, the kind of cryptography used in Verkle trees is much heavier than doing hashes. So doing hashes in CPUs is really, 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 really fast. Unfortunately, doing elliptic core operations is much slower. This is basically a trade-off of trying to make the cryptography of Verkle trees be really friendly for snarks. So yeah, it's basically a trade-off. We have done a lot of work to really make all this cryptography implementation as fast as possible. But even if we do try to do the best thing possible, it will never be as fast as the Merkle-Patricia tree kind of cryptography. So yeah, it's basically a decided trade-off. We kind of gain some benefits, but we have to pay some costs.
Cool, that makes sense. Mario, any other questions you want to surface now while we're here?
Yeah, there was a question whether the Verkle tree implementation will have a hiding property as commitments have hiding, whether it applies here.
No, it's only having binding properties, not really hiding, because hiding doesn't make sense since the state is public anyway. So the commitment doesn't really require to avoid leaking information or similar.
Right.
That's a really good question. Yeah.
Yeah, it makes sense. Yeah, thank you. Yeah, I think we can move on for now. Guillaume?
Yeah. I don't know. Can I share my screen? I don't know if it's gonna work.
Yeah, go ahead. You have the present button right here.
Share screen. Okay, so I guess it's going to share my entire screen. Wow.
Yeah, you can also upload a presentation or.
I mean, it's the same presentation. It's just that my screen might be a bit too large for for the entire thing. Okay, let me try. You'll tell me if it works or not. Here we go. Oh, okay. Here we go. All right. Does that work?
Yes.
Yes.
Okay, perfect. Yeah, so I'm going to talk about the gas changes because we change, we make pretty heavy changes to the data model. It should be obvious. So the question is, how do we update the gas model to reflect this? And the first intuition to have is that we are no longer trying to reduce the amount of I/O, right? We are no longer trying to reduce the growth of the state size, or at least more accurately, it's not that we're not trying to make this happen to prevent this. We're trying. It's not our primary focus. Our primary focus is to make the witness that stateless clients download and unpack and execute as small as possible. Then, of course, if on top of that we can, stem the state growth and ensure speedy I/O, that's better. But that's not the primary concern anymore. So yeah, what we are looking at is making sure that we reduce we look at all the actions that will increase the witness size, like reading the state. Every time you read the state, you need to prove that what you read was there and was contained the value that you claim it contained. So you will need to add it to the witness, so you will need to add it to the block, so you need to prove it. So that's an action that will have a gas impact, that will have a gas cost. Same thing with writing to the state, because you write to the state, so that there's an update of the root commitment. So you need to somehow, first of all, you need to pay for this update, so that you don't frivolously keep writing data that will increase the amount of calculation without paying for it. And one thing, I mean, Ignacio already mentioned, like, now the code is very much part of the tree, and that's because when we execute code, we need to prove that the code we execute was also part of the state, that we don't execute some random code that comes from nowhere. So we need to also change the guess model to account for what gets executed, because what gets executed is added to the witness and will make the witness bigger and therefore the block bigger. So there are really like 5 cost changes. One thing that I should say first is that when we like making the distinction of what has already been accessed as opposed to what has not been accessed is something that already exists in the current state model with the access list. So we want to reuse this scheme of access list, because once something has been added to the witness, right, the witness no longer grows. So it's only the first time that the hefty cost has to be paid. But once it has been added to the witness, it's just a matter of reading from memory cache. So we have a model that already exists in Ethereum right now. It's called the access list. And so we basically take the same model and we change the costs, except that we take some of the model of the new tree, right? If you remember, we have this way of calculating where a tree goes where a value goes in the tree. And the idea is, because the Verkle node width is 256, it's basically the last bytes, all the values that are grouped in the same 256 chunk will be next to one another. And so every time what we want to do is, every time we access one of those groups, we will pay a cost, like a hefty cost, but then every individual leaf in that group will be much cheaper to access for the first time, and even cheaper to access for the second time. And another concern that I didn't talk about, by the way, until now, is that yes, we want to fit the gas model to the new storage model, but at the same time, we don't want to break every single application out there that might have tried to optimize for a given gas model. So all those values, they might seem random, but they've actually been thought to more or less change nothing from the gas consumption perspective. From the EVM perspective, from the client perspective, it's completely different. But from the dApp perspective, it's fairly similar. It's not perfect, but it's pretty close. So the idea is that we just get rid of all the old cold storage costs that we used to have with access list, and we replace them with this model. What are the events that trigger those costs? Well, there's every time you access the state itself. So if you store, if you load. But now, if you check the balance, that also means that you have to go into the tree. I mean, okay, admittedly, that's what you already had to do, so it doesn't really change much in this respect. But yeah, so rephrasing what I should have said, every time you access the state, you like with a balance, with a self-destruct, with a code copy, you will incur those costs. One thing that changes is that we do not charge the cost for withdrawals. Withdrawals need to be added. For example, I'm saying withdrawals, but also the Denkun beacon block storage, beacon block root precompile. Actually, system contract. All those values are added to the witness, but no one pays for them. So those costs don't get charged. And it's the same thing, because you pay an upfront cost of 21,000 gas to send a transaction. We do not charge those costs for sending and for the sender and the recipient of the transaction, but everything else is charged, including, like we said, contract code. Like I said before, you only charge the first time, right? Because then the damage is done. You added data to the witness, so then it becomes the warm access cost, which is like the cost of reading from memory, and not loading from disk or any other operations like this. So basically, I don't know if Ignacio had in mind to take over here, but I can continue. I'll take it as a yes. So yeah, you have this new gas accounting. You have all new crypto, all new tree formats, all new protocols. Is this the end of it? No, because we need to convert the state. We have a state in an MPT format. There's like 1 billion leaves, so that's like 200. Okay, more like 300 gigabytes by now, or at least by the time we expect to have to start using Verkle trees. So we have to somehow convert everything, and it's not that easy because we use a different hashing model to store data in the tree. We have to rehash everything, and we've been looking at several strategies. Some of them were more centralized. Others are really decentralized, but pretty heavy on the computation. And we settled on the overlay tree, which is a method where you so you start at block just before the fork. You start with an MPT tree, right? And everything that is I'm not sure how to call it, like green blue, are values that were written to the state before the fork, and everything that is purple are values that get written to the state after the fork. So currently we are just before the fork, so there are no purple values. And we have this iterator that is going to sweep the state over time. Like it's going to, the stride of the iterator is a given value that is chosen so that most of the nodes, or at least your average node, can copy so many leaves per block without missing the slot, so being able to follow the network. And those weird red triangles represent, by the way, I forgot to mention that, the internal nodes of the MPT tree. So the red triangles are the internal nodes, and the blue-green squares are the leaves. So when the fork happens, we start with a fresh Verkle root that is considered as abstract in an abstract way. It's laid over the MPT tree, and this new Verkle root is where all the writes will end up. So if you write a new value to the tree, it's a purple value, it will end up in the overlay Verkle tree. Now, what if you and on top of that, every block, the iterator moves by n values. So here n equals 2. So yeah, the green arrow represents the head of the iterator, and it swept 2 leaves that got moved, or more exactly copied, into the Verkle tree. And now if I want to look for the pink square, which is currently in the Merkle tree, what we do is that we first try to read from the Verkle tree. We do not find it there, so we go to the Merkle tree, which is read only, and we find it there. And we continue this way. So the iterator at each block, the iterator continues copying values, and you can see that, for example, one value that used to be in the MPT has been clobbered. It hasn't been clobbered. It's a value that was copied from the MPT, but has been overwritten. So the MPT is frozen; it doesn't change, but the values themselves keep getting copied, unless, of course, they overwrite a new version of that value. And eventually, or at least when the fork block has been finalized, you can afford to delete all the MPT internal nodes, so you're freeing a lot of space. And I'm sorry, I don't know what happened with the with the slide, with the formatting here. But the idea is that when all the leaves, because the iterator keeps progressing, eventually, and because the iterator keeps progressing and the MPT itself is read-only, eventually all the nodes will be all the leaves will have been moved to the Verkle tree. So you can afford to delete all the internal data. And one thing, like this model is a bit simplified, so I did not really represent that on those slides. But what you have to know is that currently I represent the copy, the leaves in the MPT and the Verkle tree as being in the same order, but they're not. This is just a simplification. So yeah, this is the gist of the method. The question is, how do we set the stride of the iterator? And we have a bit of a model, and basically it looks like we can afford what we want is it's a trade-off between how many leaves we copy per block and how many machines, what part of the network we are comfortable with losing during the transition. Of course, we cannot afford to lose more than 1/3 of the network. That would be critical. But we can see that already with 5,000 leaves, we're definitely not losing too many. We can afford to lose, more than 20% of the network, and still complete the transition in 2 months. So I think by now, given the test we've done, we're pretty comfortable doing 10,000 leaves. So we would be 10,000 leaves per block. So we would be able to proceed with the conversion within 15 days, which is not too bad. But yeah, ultimately we need to do more testing. We might even discover that 20,000 leaves is okay, because as we go more, the machines connected to the network are more and more powerful. But yeah, this is not exactly an open question, but it's still a parameter that can change before the fork. Right. So once again, Ignacio, I don't know if you plan to talk about this, but I can do it. Okay. So like I said, we sorry. Yep. Hello. Okay, I'll continue. So like I said, we have to rehash everything. But the problem is that so far, not everybody has stored. In fact, a very, very small majority of people have stored pre-images of all the key hashes in their databases. It's like 70 gigabytes, more or less. So yeah, why would you take up 70 gigabytes if you don't have to? The problem is that for the transition, you have to have them. So we don't really we have to find a way to distribute those pre-images. And to do this, we have looked at several steps, several methods. But the fact is that Erigan and Reth store their data by pre-images. By pre-images. So they have the ability to generate a file that they could then distribute. And it's not as bad as, for example, converting the entire database, because the entire database is very large. The verification, if you are given the pre-images, you can go over your own database and verify that you've got all the pre-images. So it's much cheaper and much safer to distribute. But the consequence would be that you cannot exactly start the sweep right away. You need to have some time to get the pre-images generated, like the pre-images of the frozen Merkle tree, distributed. So we would give ourselves a week, during which the Verkle tree gets written too, but no conversion happens. So we still have the two trees. And when this when a client receives the preimages, it can very easily verify that it's got all the preimages it needs, because it's only the preimages of a frozen Merkle tree. And then the sweeping start. And if we find, of course, that there's a problem in the preimage distribution, we can always make an emergency release. It's not really great, but it's we have a way to handle that. But yeah, it's still kind of an open problem, but it's not doesn't feel like a big one, so we're not losing sleep over this one. And then the last thing I plan to talk about was how we sync. So there's currently there's only one client that has sync implemented, which is a Verkle version of SnapSync. But what I want to give you is an overview of what you could do with Verkle trees, how Verkle trees would simplify the sync. And the idea is that you already have parts of the tree packaged in every block. So the idea is to leverage this feature to solve the sync and make sync much simpler. So you would start at block N, the block you join the network at, and you execute statelessly. But as you go, you keep rebuilding trees, so you can actually accumulate all the leaves, and you have the latest version of a leaf, which is always the biggest problem with the sync, because you are given the latest view of the tree. So if a leaf hasn't been touched, it means you have the latest version. Simply, it's from a previous block. And then what you do in the background is you start downloading, you start asking nodes around you, full nodes around you, for all the leaves that have not been seen in the stateless view so far. And you can verify them very, very easily, because every time it's only going to be a small subset of the tree, so you can recompute the root commitment very, very fast, at least comparatively fast, and verify that what you've got is the current state, at least fits in your current view. And and once again, it doesn't even matter how long this process lasts, because you can keep executing blocks statelessly until that point. So yeah, that's pretty much the idea. I think that was Ignacio, I'll let you conclude.
Yes, can you hear me?
Yep.
Okay, because I had a problem with my mic. Yeah, this is kind of the end of the presentation. I left here an image on like why we use an elephant for Verkle trees, which might be surprising or not really obvious. So I learned from Guillaume that elephants are known for, destroying branches of tree or uprooting trees, which really is pretty related with what we are trying to do for the Ethereum protocol, of changing the Merkle-based tree with another tree. So I think this elephant kind of mascot was a really good idea from, I think, Guillaume and Parry from the DevOps team. So
Yeah, that was totally Parry.
well, yeah, great to him. And I think that maybe Josh wants to say something else.
Yeah, just really quick. Well, thank you to Ignacio, Guillaume, everyone here. Ignacio and Guillaume, just wanted to emphasize that they've been doing a lot of heavy lifting on Verkle for a long time. So a lot of appreciation to their work and many others who are working on Verkle. I'm here happy just to play a small part. And also for anyone interested, we have bi-weekly Verkle implementer calls. Anyone is welcome to listen in, of course. If you want to take a more active role, feel free to drop a message in the Ethereum R&D Discord. There should be a link handy. But yes, bi-weekly calls where we continue these kinds of discussions.
Awesome. Thank you so much, guys. Very well. I think we can conclude the presentation. Let me see if there are any questions for you before we wrap up. Yeah, thank you so much, all three of you. It was really great, Ignacio especially, and with all the deep dive cryptography, and Guillaume with the gas pricing, with the migration. Thank you so much. It's a lot to digest, but I believe there might be some questions. One thing which was asked before was about the post-quantum security, whether Verkle improves the situation, whether it's makes it maybe easier in the future to swap for something quantum secure.
Yeah, so the reality, as we discussed there in the chat, is all the elliptic curve-based cryptography isn't really safe for like quantum computers. So actually, we have like, yes, I mean, Verkle tree cryptography isn't safe for quantum, so that's period. But that we also have to do other kind of changes in the protocol, like the signatures that we use for transactions is elliptic curve based, so we will have to change the way that signatures work. KCG commitments using blobs also use elliptic curve based cryptography, so that will also break. So usually the plan that the way that we think about cryptography and this problem is every cryptography used in the protocol should have a candidate that is quantum safe, and any new cryptography that we plan to use or introduce now should have an alternative that we can change in the future. The thing with this is that this quantum cryptography is usually pretty new, at least compared to the more solid cryptography that we use now, and also it's much slower and has other trade-offs like bigger signatures or things like that. So it's not really like a simple choice to say, hey, just simply use quantum safe cryptography. That has other trade-offs that will impact UX or have other effects that will be pretty bad. So whenever this risk becomes really closer to being practical, let's say, then we should really start switching this kind of unsafe cryptography to other schemes.
Right, but that's the point. The work we do now might have to be redone, but at least we'll have done it once, so we'll understand what's going on. And we currently, it makes complete sense to focus on elliptic curves because, well, first of all, it still remains to be proven that quantum computing is really around the corner, and that's more importantly that they can break elliptic curve cryptography. But when this happens, we'll be ready to switch again.
Yeah, awesome. Yeah, it makes sense. I think thanks so much to both of you. The question on the like computational overhead, there's two questions here, but maybe we can merge them. So MPTs have a branching factor of 16, while Verkle trees have 256. Are there any benchmarks, links, or any analysis on trade-offs for bandwidth computation? And another question for around the computation is on the transition on the node transitioning to the Verkle tree. How much heavier machine is needed for this?
Yeah, so regarding the branching factor question, so the special like where the magic happens for Verkle trees is that the branching factor doesn't have an impact on these openings that we have to do on each node or on each vector. There is still a trade-off there because the branching factor. So in inner product arguments, the proof size and the verification time. The verification time is linear on the size of the vector, so we cannot really like simply select a branching factor of 1 million and store everything in a single vector. So there's still has to be a balance between the branching factor and the cost of doing openings for verifying openings for verifiers. So yeah, and from another perspective, increasing the branching factor makes the tree shallower, so that requires like less elements in the proof. So yeah, you have to do some kind of multi-factor analysis on like verifying time for proofs and how much that helps the depth of the tree and things like that. So yeah, I know maybe the other question regarding state conversion. So maybe Guillaume wants to complement this later, but we have done some benchmarks on, like usual desktop machines and also on Rock 5e as a lowest setup hardware. And I think that we feel comfortable around migrating probably 10K key values per block, even in a Rock 5e. But the benchmark that we did at that point in time didn't include 4844 load in mainnet because it didn't exist. So probably we'll have to do some new benchmarks to really understand how like the current mainnet load, how much like performance or like resource lag it leaves to really add this extra work of doing the conversion per block, or even decide if Rock 5e or these really low setup machines are really are reasonable expectations for nodes to be really run this conversion. I don't know if Guillaume wants to say something more.
No, that was pretty much it. I seem to have understood that there was a bandwidth question. So the point is that it's the average size for the proof is 150 kilobytes. So we're doing way worse than that with blobs. So we don't really. I mean, we haven't really done any benchmarks to this, but that's because we don't expect it's nothing. So it's not really we don't expect any issue with that.
That's interesting. Thank you so much. I was wondering how it will look like in the setup of the stateless clients for nodes, whether there will be like a more overhead of the peer-to-peer network. So that's it's interesting to hear. Awesome. And maybe the question about like generally what are the current tasks, what are challenges right now, what is being solved, what is the roadmap, and maybe whether there are some parts that people could look into start contributing to.
I mean, the current roadmap is sync and conversion and pre-image distribution. Contribution. Well, there's several areas. The one that would be my favorite and never gets attention is implementing Verkle trees in other clients. So we have a pretty complete implementation in Geth, in Nethermind and Ethereum JS, but there's no implementation to speak of in Wrath. In Aragon, it's pretty nascent, so that I'm sure they could appreciate some work. And forgetting one, Besu. Besu is on the way, but I'm sure they would appreciate some help as well. Otherwise, what's an area to contribute to? Well, we want to build stateless clients, so stateless clients are an option. And otherwise, something that is also not receiving a lot of attention, it's not directly core protocol related, but it's how L2s, dApps are going, like compilers, are going to handle Verkle tree specificities, especially compilers. There's no work done on compilers at the moment. So that would be an extremely useful contribution. And then otherwise, I mean, there's plenty of tooling required. We don't really have a lot of support in block explorers. There's also some work that can be done, although that was already the topic of one of EPF EPF efforts last year. But there's always the ZK stuff. This one I think is a bit too early to be realistically helpful, but that's an option. There's state expiry, very good work done by Han last year. So yeah, maybe see how it interacts with account abstraction. If you can build relayers, there's a ton of things to do. Honestly, I wouldn't name one that's the most important. Everything is important. Maybe Ignacio has more ideas.
No, I think I agree with all that list. I mean, we have other, like the previous distribution and all that. I think we have more like decisions to make than really executable tasks. That we want to like get more feedback from client teams and what kind of solutions might make them more comfortable. But I think it was a really nice list of things that people can contribute.
Awesome. Yeah. Thank you so much, guys. We are running through almost all the questions, I believe. There's some being answered in the Discord as well. Thank you so much for joining the Discord, by the way, and answering there. We really appreciate it as a study group. You mentioned the state expiry, and it's something that I wanted to ask about, like, because the state expiry used to be a bigger thing, and now it's just in the background. It's not really mentioned much. So, do you think that the Verkle trees also open the gates to state expiry? Is it going to happen? Is it more feasible with the Verkle trees? Like, what is the benefit there? Or
yeah. So yes, it totally makes it feasible, or at least more practical. It's the problem with Verkle trees is that it's both a boon and a bane for state expiry. It's a boon because the proving system makes it so much more practical, but it makes it less relevant at the same time because state growth becomes less of a problem. So if state growth becomes less of a problem, it's less of a requirement, or at least an emergency. But there's been some very good work done by Han last year, and I think, in fact, I need to get back to him about the topic. I think we have a good streamlined solution. So there's no implementation to speak of currently, but at least there's been good work done at the theoretical level, such that I think it would be interesting to keep digging in this topic, but knowing that, once again, unfortunately, Verkle trees make it less likely that this will be adopted in the near future because it's not as urgent, but it's definitely a topic that we'll need to face sooner or later. So it's I don't think it spells the doom of state expiry. It's just that, yeah, it's still no one really cares about it at the moment. That would be its biggest problem.
I care about it. I asked about it because, like, I was excited, or like, I liked the proposals when I first ran into it, because there is just so much useless stuff in the state that my node needs to be running, right? Like, I my precious little machine, and I store so much unimportant things there, which could expire hopefully. So, and even in the stateless era, I'm going to run as full node as possible. So it would be nice to have more lean.
Right, but between history expiry, because most of the stuff that is taking space on your disk is actually the blocks, the historical blocks, the receipts, all that stuff. So we have history expiry, which is another big topic. I'm not really helping my case here, but that's also a very important topic. And this one, some of it we could even do now. Like, we store the receipts forever. Do we need to? Not really. We could. Geth has been working on getting rid of the historical blocks. But other clients might be interested in implementing history expiry, and that's a very interesting topic too, because you don't really need a hard fork for that. You just need to implement it. That's it. there's a few problems with it, and okay, I'm gonna stop talking about history expiry, but that would have a major impact. And then on top of that, Verkle trees would have another major impact, because the tree, we found ways of storing the tree in such a way that it's also going to take less space, at least theoretically. So once you have those two things, history expiry becomes way less of a problem. It's still, you're right, there's a lot of stuff that is completely pointless. When in 50 years, who's going to care about your CryptoKitties, right? Most of the people owning CryptoKitties, okay, maybe not in 50 years, but in 100 years, most likely everybody owning a CryptoKitty will be dead. Do we still need it? No. And more importantly, we'll be running out of people who care about CryptoKitties. So yes, it's quite important in the long run, but in practical terms, in the next 10 years, you will not need state expiry, basically.
Great. Yeah, thanks so much for giving the intro into the history expiry as well, because it's kind of a teaser for a talk later in the study group. We'll have Piper talking about history expiry in the full talk, so we'll dive into that as well. Thank you so much, Guillaume. And folks, I think there are not many other questions that we can answer now. We have maybe a few more minutes to go. Josh, do you have anything?
So Verkle is sort of slated for the following hard fork after the next one. What's sort of like the time frame you see for actually having all this stuff implemented in different clients and benchmarked and tested and all of the things ready for a hard fork?
I was hoping to give the floor to Josh. Okay, I'll just give a quick update. So I'm extremely optimistic, right? I still believe we can front run Denkun. So this is to tell you how optimistic I am. But from what I see, most of the problems have been solved. Yes, there's still a few open problems like sync, pre-image distribution, but this is really a problem because a lot of clients have not looked at have looked at other things instead of looking at Verkle trees. But there's been a lot of progress with clients. Like, we have a good support in Nethermind, we have a pretty good support in Ethereum.js. Besu is on the way, like they're making progress as well. I think next year, like a year, is realistic. Maybe someone more pessimistic would say a year and a half, 2 years, but it's definitely ready for its prime, at least.
Awesome. Well, congratulations on that, and good luck front running Denkun. But
thank you.
Yeah, amazing. Yeah, thank you so much, guys. Well, thank you so much for the presentation, but especially all the great work you've done on the Verkle tree migration, on the whole concept. It's great to learn from you. We are almost at 90 minutes. I think we can wrap up here. But again, we really appreciate having you here. We appreciate having you in the Discord answering questions. Maybe if there are some more questions coming, like keep an eye on it. People might ping with something, and I hope that you folks listening to this learned a lot, and we will have some more documentation on the wiki for Verkle trees later on. Yeah, awesome.
Great. Thank you, everybody. We will see you all next Monday for a dive into consensus layer client architecture with Paul from Teku. And thanks again, Guillaume, Ignacio, Josh, for your time today.
Thanks.
Appreciate it. See you guys. Bye-bye.